Okay. Welcome, everybody, to lecture 25 of CSE 548, the analysis of algorithms. Before I get started, are there any logistical questions about the course or about any of the questions about any of the homeworks or anything we've done so far that comes on? Question? Are you going to discuss the final at some point? Am I going to discuss the final at some point? The answer is yes. Okay? But that point will probably be like the last class. Basically, I'll talk about the final, the last class of the semester. But in principle, it's going to be a inclusive final, include everything that we've covered. Okay. There may be a minor bias in terms of percentage of the test covered towards what we've covered since the last midterm, which would be basically the NP-completeness stuff. But basically, it will be a comprehensive final, usual open book thing. It will be designed to go 3 hours, but less than. My hope is to make it less than a tiny bit less than the equivalent of 2 midterms, so that somehow, since the midterm was supposedly taking an hour and 20 minutes, 2 midterms would take 2 hours and 40 minutes. If I make it a little bit less, that gives you half an hour of slack or so. So my vision is to make it a little bit shorter. So maybe there's a little less time pressure on the on the final. It'll be open book, and the problems will be like the kind of problems that you've been used to seeing. Okay? So if you've done well on those, you shouldn't be worried. If you haven't done well on those, it's a good time to start studying. Go back, look at the old homeworks. Okay? Look at the solutions to the homeworks in the library. Try to figure out where, how you get from point A to point B. Okay? And we'll see. But it will be inclusive, and it'll go back to what we've covered from the beginning. Question? What is the location of the final? For that, we'll tell you the last class of the semester. I don't remember. I have some vague idea. It's in the chemistry building. But don't trust me on that. Show up the last class. Question? Will you post a sample final? I will presumably post a sample final, although even if I don't, it's sort of you have the equivalent of a sample final, given that you've got a sample midterm 1 and a midterm 2. Okay? And you maybe could extrapolate to the other. So I may post a final, though I tend to like to keep finals private. Okay, so that might not happen, but it shouldn't be a mystery to you what a final looks like. Okay, any other questions about anything we've covered so far? Any other logistical concerns? Okay, that said, we've been talking about NP-completeness. And last class, we proved that vertex cover was hard, using a very, very clever reduction from tree satisfiability. Okay, are there any questions that come to mind about that reduction? Or that's a reduction that you should look at and admire and try to figure out how it works. Okay, but that requires a considerable amount of cleverness. Okay, a lot of reductions that you see can be very clever and very complicated. Now, the reason is because, remember, what is an NP-completeness proof? We're translating our hard problem, known hard problem, into the problem that we're interested in figuring out. And if the known hard problem is in some sense structured quite a bit differently than the problem we're interested in, you would expect the translation would have to be fairly baroque, okay, fairly complicated. Okay? The important point, though, is that as we start to build up a repertoire of NP-complete problems, okay, that we know are hard, okay, sometimes it's easier, and quite often it's easier, to start from a problem that we know is hard, that looks a lot like the problem that we want, and then the reductions are not so complicated. Okay? So this is where we can start to get into reductions that mortals can hope to figure out. Okay? Question? Can I make the screen a little lighter? Probably not. Let's see. Does this do anything? Does this do anything? What? Don't do anything. Don't do anything. Okay, let's go back here. Sorry about that. This is bad for the folks back home. Okay. Have I fixed the screen for the folks back home?
Tilt the far one down.
This one?
Yeah, down.
And is everything else okay?
Yeah.
Sorry about that for the folks in TV land. Okay. How bad can people read it now? Okay. Or if not, maybe they can do something with the lights, but I apparently don't have any control over it. Okay, so what is the situation? We want to now start to prove other problems are hard, okay, using what we know. So let's take a look at another famous graph algorithm problem, that of finding a maximum clique. Okay, what is the maximum clique problem? Our input is a graph and an integer, j, which is less than the number of vertices. And the question is does the graph contain a clique of j vertices? Meaning a subset of vertices, of j vertices, such that every pair of vertices in the subset is an edge in the graph. So for example, in this graph here, okay, this graph contains a clique of size 5. Why is it? Because if we take these 5 vertices, okay, every pair in there is connected. Okay? And the clique problem is, given a bound in a graph, find the clique of that time bound. Okay? Any questions about that? Okay? First thing, how would you find a clique, tell whether a graph contains a clique of size 2? Can somebody give me an algorithm to tell whether a graph contains a clique of size 2 that is very efficient? Okay? Question? Check if there is an edge. Okay? If there is an edge, that means you've got a pair of 2 vertices and every edge between them is connected. Finding a clique of size 2 in a graph is an easy thing. Okay? How would you find a graph of size 3? Well, a clique of size 3? Well, you could try all triplets of vertices. Okay? And then check to make sure that all possible edges are there. Okay? But in general, the problem is find the clique of size j. Okay? And this problem, where the size of the clique is an input, okay, and potentially very large, is where the clique problem gets to be hard. Okay? Any questions about cliques? Yes?
Is this the same as find the complete subgraph?
This is the same as finding the largest complete subgraph. Okay, a clique is a complete graph. So this is asking for what is the largest complete subgraph of the unknown, of the graph. Okay? And again, such a thing can be useful in pattern recognition. Again, I mentioned, I think, earlier in the semester about this application on detecting fraud in income tax. Okay? Where really what they did is they wanted to see if somebody was sending in a lot of income tax forms which are exactly the same, okay, that would correspond to a clique of income tax forms in the total graph of income tax forms, when you add an edge if 2 forms are pretty close to each other. Okay, so that's how they nail them for tax evasion. Okay? Although the problem we will show is NP-complete. Okay, it turns out they look for very small cliques. Okay, and that's how they can get away with it. Okay, any questions? So how do we prove that clique is NP-complete? Okay? First question is, what problems should we start with? What problems do we have that are hard? We have satisfiability, we have pre-satisfiability, we have vertex cover. What is likely to be the easiest problem to start with? Vertex cover. Why? Looks like a graph. Okay? You want to go in vertex cover, you've got a graph and a bound. Okay? Namely a cover of size k. And in clique you have a graph and a bound. Okay? So now hopefully the translation from that to that will be easier than doing a lot of monkeying with logic formulas. Okay? So how do we prove this thing? Okay? The proof turns out to be actually quite easy, okay, once you see sort of a nice intermediate step. Suppose we have a graph, okay, and we find that it's a vertex cover of that graph. Okay? So for this particular graph here, my claim is these 4 square vertices forms a cover of that graph, right? Because every edge is going to touch on at least one of those 4 vertices. What is interesting, if we have a vertex cover of those square vertices, the square vertices form a cover, what is true about the black vertices? Okay? The black vertices are all the vertices that are not in the cover. Okay? Can there possibly be an edge between 2 black vertices? No. Okay? The answer is no. Why is that? Because the square vertices form a vertex cover. A vertex cover, by definition, has an endpoint on every single edge in the graph, correct? So if we take every vertex that is not in the cover, okay, there can't possibly be an edge between them because that edge would not have an endpoint in the cover, okay? So what's interesting here is we say that a set of vertices is an independent set, okay, of a graph, okay, if there are a set of, if there is no edge between any pair of, between no pair of vertices in our set. So for example, suppose, let's say you had a group of people and you had a friendship graph defined on them. If you found an independent set of the vertices in that friendship graph, what are you defining? Okay? An independent set, remember, is a set of vertices where there's no edge between any of them. So in a friendship graph where there was an edge between any two people which were friends, an independent set would be a group of people, none of whom know each other. Okay? Any questions about what we mean by an independent set? Okay? What's interesting, though, is since everything that is not in a vertex cover is an independent set, if you found the smallest possible vertex cover, what are you really finding at the same time? The largest possible independent set. It's not hard to find a small independent set because if you just take one vertex, they have no friends there. Okay, so one person's an island. Finding an independent set is a trivial thing. Finding a large independent set, okay, seems to be a hard thing. Okay, and we can prove that it's a hard thing by this sort of a simple observation. Since the complement of the vertices of any vertex cover forms an independent set, okay, we know that if we want to find the largest independent set, that is equivalent to finding the smallest vertex cover. Okay? And so lo and behold, maximum independent set problem is exactly the same problem, okay, as finding a minimum vertex cover. If you find one, just take all the vertices that are not in that and call it the other. Okay? How many people believe that? How many people do not believe it? Okay? Unanimous. Okay? If you do that, then I've just proven a problem NP-complete. I've just proven that maximum independent set must be NP-complete. Why? What was our known NP-complete problem? Okay, it was vertex cover. What would be my algorithm for independent set? Okay, vertex cover of G. I could find the independent set of G, okay, the maximum independent set of G, and return n minus the size of this maximum independent set. Okay? So if I had a fast algorithm to solve maximum independent set, that would give me a fast algorithm to solve vertex cover. Okay? Since I don't have one for this, I don't have one for that, I've just proven maximum independent set is hard. It can be that easy. Okay? So any questions about why maximum independent set has to be hard? Okay? Simple reduction. Okay, now we have another NP-complete problem. But what we wanted to know was the Clique problem. What was the Clique problem? The Clique problem, we were looking for a large number of vertices, all of which are connected, correct? What does the independent set problem give us? Okay. A large set of vertices such that all of them are disconnected, correct? Okay. So what is the idea here? Okay. These problems are actually fairly closely related. The point is that a clique in a graph, if you took the complement of that graph, meaning you changed every edge into a non-edge, and every non-edge into an edge, the role of clique and independent set get reversed. So suppose we took this graph here, which we'd shown before. Okay? Here was our graph. Suppose we took the complement of this graph. What edges are not in this graph? Well, there's no edge from here to here, and there's no edge from here to here. This was a clique, so there's all edges from here to here. Okay? My claim is the complement of this graph would be this graph. Okay? Because I've taken everything where there was an edge, delete it. Everything where there was not an edge, add it.
Wait, I'm sorry, say that again?
Okay? The complement operation changes every edge to a non-edge. This was an edge, now it's a non-edge. And every non-edge to an edge. Okay? So in this graph, this is the graph. What do we know about this graph? What's the largest clique in this graph? 5. What's the largest independent set in this graph? Set of vertices that are not connected to each other mutually. 2. Why? This one and this one. There's only 2 edges in the graph that aren't there. There's this edge from here to here and this edge from here to here. But this edge does exist. Yes?
What about that vertex on far left?
Far left?
That doesn't have a joint edge to the far right edge.
Okay, so you're saying that there should be an edge in the complement clique from here to here. Right there. Okay, let's look at what edges there are here. In the complement, there is no edge from here to here, so we add that. There is no edge from here to here, so we add that. Is there any other edge in the complement of this? Okay? Think about it this way. There's 6 vertices. Okay? This vertex is of degree 5, so it can't be involved with anything. This vertex is of degree 5. It can't be involved with anything. This vertex is of degree 5. It can't be involved with anything. This is of degree 4, so it can only be involved with 1. Degree 4 can only be involved with 1. Degree 3 can be involved with 2. So this is the complement. But what's interesting about this? In this graph, the maximum clique is 5. The maximum independent set is 2. Something like this and this would be a maximum independent set. Correct? What's true about this graph? Okay? What's the maximum clique in this graph? What's the maximum subset of vertices such that all pairs are connected? 2. No, not 3. Bop, bop, bop. It's not a question of whether the graph is connected, whether all pairs are connected. That's what we mean by a clique. So, and this is not a clique. This would be a path. If we had that edge, we'd have a clique of 3 or a triangle. Instead, the largest clique we have here is this. What's the largest independent set in this graph? 5. And it corresponds exactly to the complement of the clique. So what's the point? The complement of an independent set is a clique, and vice versa. We know that it is hard to find a maximum independent set, right? We proved that a second ago. How do we now prove that it's hard to find the maximum clique? Well, we do a reduction. Maximum independent set, okay? To solve maximum independent set on G, we're going to want to say G and K, okay? We want to now solve a clique problem on what graph? If we take the complement of this graph and then ask for that. Let's go down a little bit. To find the maximum independent set of a graph G on K, we complement it and then find the clique of size K. If we can, we found the maximum independent set. If we can't, we can't. This problem is hard. What does that mean about this problem? Has to be hard. So I claim I've just proven clique is NP-complete. Okay, without working up a sweat. Okay? Any questions about these reductions? These are the kind of reductions that potentially you should be able to see. Okay? So, so question.
Such reductions from a known NP-complete problem to an unknown NP, what is the best suggestion to
So how do you pick a problem? Okay? My sense is, again, the basic goal you're looking for is to pick the problem that looks most like the problem that you want to solve. Okay? Now, there wasn't any doubt. Everybody here had no question that vertex cover was going to be the right place to work from for the start. Okay? As you get to know more and more NP-complete problems, it probably gets to be harder and harder to pick the right one. For that reason, what I usually do is I limit my attention to a very, very small number of NP-complete problems. My favorite NP-complete problems for proving problems hard are free satisfiability, okay, vertex cover / independent set / clique. These are all sort of basically the same thing, okay. Hamiltonian cycle, given a graph, find out whether there's a way to visit every vertex exactly once, okay. Originally, I was thinking about proving that one hard this semester, but I probably am not going to do it in class. It's in the textbook. It's, another kind of Baroque and elegant construction, okay? But once you've seen it, you now know Hamiltonian cycle's hard. And the other problem I will use is integer partition, which I'll prove hard in a second, okay, which is a number problem. That's basically all that I work from, okay? And when you're only working from these few problems, it's fairly easy to identify what the closest one is. Okay? Other people have different strategies. That's the way I do it. Okay? Any questions about that? Okay? So think about these reductions. You should be able to prove that all of these problems are hard. Okay? That clique and independent set are hard given vertex cover. And that's the kind of strategies that you're going to be wanting to do. Okay? Because that, I think, is something that's a reasonable idea. Any questions? Okay? So that said, let's now prove the problem of the day hard. What was the problem of the day? The problem of the day asked, prove that subgraph isomorphism is NP-complete. What is subgraph isomorphism? We're given a graph G, okay, and a graph H. Okay, like let's say that, for example, G might be a graph that looks something like this. Okay? And we're given a graph H, that's G. H might look something like this. Okay? And the question is there a place where H is contained in G? Okay? This graph has 5 vertices. This graph has 4 vertices. Is there a place where H is contained in G? Okay? If you label these vertices 1, 2, 3, and 4, if we label this 1, 2, 3, and 4, there is an edge in here for every edge in here, and vice versa. Okay? So this is isomorphic to it. Okay? If we add an edge like this, is this subgraph isomorphic to that? No, it doesn't contain it. Okay? So what's the problem now? Prove that subgraph isomorphism is NP-complete. What is the problem we should start with if we want to prove the problem is hard? Which problem do you know that sounds and smells most like graph isomorphism? Is it satisfiability? Is it vertex cover? Okay. Is it maximum independent set? Is it clique? Okay. Clique. People are starting to see clique. Okay. Why is that? Clique makes this problem trivial. What do we want to do? We want to prove that we can solve clique, okay, of G comma K using subgraph isomorphism, right? What are the arguments to subgraph isomorphism? 2 graphs, right? What should one of those graphs be? Okay? One of them should be the graph that we input, okay, to our clique problem. What would the other graph that we'd want to look for be? Okay, the complete graph. Suppose I give you as arguments to subgraph isomorphism the input graph and another graph, which is the complete graph on k vertices. What is subgraph isomorphism asking? Is this contained in that, right? So, my claim is this is contained in that if this contains a clique. That's trivial at this point. Okay? So the general problem of subgraph isomorphism has to be hard, because even the simple, quote-unquote, simple problem of just testing if that second graph is a complete graph is hard. Okay? Question? What the problem is saying is you're given two separate graphs. Okay? You're given a graph G and a graph H. Here's what your input is. Here's a graph G, here's a graph H. And you're asking, is there a copy of this in there? The hard part is finding the copy. Yeah, question?
Does it also mean like a subgraph of H is a subgraph?
Right. That's okay. There's two different kinds of questions that you could be asking now. Okay, which is a good point. Okay. When I say that one is a subgraph of the other, okay, there's two different kinds of subgraphs that can be defined. So, for example, suppose let's say our graph G looked like, let's say was a triangle. Let's say this was our graph G was a triangle, and our H graph was just a path on 3 nodes. Okay? Is this graph a subgraph of that? It is if you're allowed to delete an edge from G to make the matching. Okay? And so, in fact, there's two different notions of subgraph isomorphism. One where you're allowed to delete an edge, one where you're not allowed to delete an edge. It's called the difference between subgraph and induced subgraphs, if you really know your graph theory. Okay? But why didn't I bother to explain that to you? Because my claim is this proof proves that both subgraph isomorphism and induced subgraph isomorphism are both hard. Because in this case, you don't ever want to delete an edge from the original graph, because all you're looking to do is match something that's complete. Okay? So not only did I prove subgraph isomorphism is hard, I even proved induced subgraph isomorphism is hard. Okay? Where you have that extra degree of flexibility, because I showed that extra degree of flexibility can't help you. Okay? So once you get into this game, it becomes very, very easy to accumulate lots and lots of NP-complete problems. Okay? There's a lot of hardness out there. Okay? And you can usually figure it out by just sort of tweaking things. Okay? Any questions about this kind of procedure? Okay? These are the kind of things that I think you can figure out. These Baroque constructions are worth watching and worth admiring. Okay? And they require practice till you can do them. Although they're actually not as hard. Once you get into the mindset, they're not as hard as you might think. Okay? But this, you should be able to see where these kind of things are coming from. Any questions? Okay? That said, let's go to another Baroque construction. Okay? One of my other favorite NP-completeness proofs. Okay? Which is, we've proven graph isomorphism is hard. Clique is hard. That's a graph problem. We've proven that free-sat is hard. That is a logic problem. Now let's prove that a number problem is hard. Okay? And a classical number problem is called integer partition or subset sum, depending upon, different people call it different names. What is the problem? As input, we're given a set of integers and a target integer. Okay? And the problem is there a subset of the input integers which adds up exactly to the target? Okay? So, for example, here might be an input instance of our problem. Here I've given you a specific set S of input integers and a target number there. The problem is there a subset of these numbers which add up exactly to that? Okay? It probably isn't obvious when you take a look at this problem, but in fact this does have an answer, because if you pick 1, 16, 64, 256, 180, this, and this. That adds up to 37, 40, 54. Someone can check that on a calculator, and hopefully it'll be right. Okay? But this is an example of the subset sum problem. Okay? And subset problem, now you may say, well, why would this come up? Okay? In various disguises, this problem comes up in a lot of circumstances. Okay? One sort of maybe fanciful illustration of this. Suppose you're given a gift certificate for $300 at a particular store. Okay? And you want to use this gift certificate to its maximum amount. What do you want to do? You want to go to the store, find out the price of every single object there, and ask, is there a set of objects you can buy that will use up your gift certificate perfectly? That is the subset sum problem. Okay? How many people see what I mean by that and agree that that's the problem? Okay? That may not sound like a real application, but this is very, very close to a lot of problems, for example, in packing things up. Suppose, let's say, you want to fill up a truck, okay, as full as possible. And these are, let's say, the weights of the objects you can stick in the truck. How do you put as much stuff into the truck as you can? Okay? So there's lots of packing problems that are really this thing at heart. Yeah?
It also sounds a little like you have a certain amount of money allocated for a business and you want to invest it as best as you can.
Another allocation, maybe this is an allocation problem. That you have a certain amount of money and you can spread it out in certain ways. Okay? What's the best way to do it? Okay? That's very close to the gift certificate analogy. Okay? Maybe dressed up a little bit. Yeah?
What about exact change?
What about exact change? So is this way of modeling an exact change kind of thing? I don't. Okay, I'm not sure I see whether this is quite. Okay.
On the bus, you get so much money in your pocket.
Right.
And you have to give exact change.
Okay, so now what you've got is, okay, you go onto the, right, okay, right. I guess another way to model it is this. You're right. You go into the bus. You've got certain different denominations of change on you. They demand $1.56 to ride the buses in a particular town. Can you make exactly $1.56, or they'll throw you off the train, or throw you off the bus? How do you go and do that? That again is another example of integer partition. So this is a real problem at a very abstract level, okay? And variations of this are very important, okay? But how easy or hard is it to get on that bus, to stay on the bus, okay? The answer we'll prove is that it's NP complete. So if you're going to get on the bus, you'd better make sure you have the exact change beforehand. Yeah, question?
Well, when you say with the change, it's only like dime,
So you're saying here is on the bus problem, you only have dimes, nickels, and quarters. That's something you're now assuming about the way that change works in that country. Okay? There may be countries where, let's say, that to appease the, let's say, local parliament, they want to have a different denominations coin with everybody's face on it. There might be lots of different denominations. Okay? So abstractly, the problem is a change problem. You may say that that problem is, well, that's easy because you only have a small number of types of change. Okay? But now you're putting an extra restriction on it. If you restrict the problem, a hard problem, it may become easy. Okay? But without that restriction, we can prove that this problem is hard. Okay? How do we do it? Okay? Now, we need to come up with a reduction from a known NP-complete problem to integer partition. Okay? When we finish the translation, we're going to end up with numbers, okay, representing to our set numbers, and a target number. Okay? What is that target number? Okay, it's a separate number. Now, what should we start from? Okay, here it may not be quite so obvious. We could start from the logic problem or the graph problem. My claim is it turns out that an easier reduction will follow from the graph problem. Okay, although this maybe wouldn't be obvious, okay, but it's a slick reduction. How are we going to do it? Well, one way we're going to do it is to show that vertex cover reduces to integer partition. And how do we do this? Well, vertex cover is a problem that gives us a graph G and a target integer K. Correct? Come up with a vertex cover, a cover of this using at most K vertices. Okay? what we're going to do now is convert that graph into a set of numbers, okay? And in order to do that, we're going to start by converting that graph into some kind of a data structure called an incidence matrix, which isn't really that complicated, okay? It's actually kind of a nice way to think about graphs. Here we've got a graph. This graph has vertices 0, 1, 2, 3, 4, and 5, right? It has edges 0, 1, 2, 3, and 4, right? We can create a matrix where the rows are vertices and the edges are columns, okay? And we will have a 1 whenever whenever a vertex contains an edge, touches an edge, okay? So what is the row associated with vertex 0? Vertex 0 is adjacent to which edges? Okay, edge 0, edge 1, edge 2, edge 3, but not edge 4, right? So sure enough, we have a 1 between vertex 0 and everything except edge 4. Okay? Edge 4 is adjacent to which vertices? 2 and 3. So if we look at the column corresponding to edge 4, there are 2 1s there corresponding to the vertices that define that edge. Correct? Okay, any questions about incidence matrices? Okay, if you have a question, it's a good point to ask. Okay, how many people feel confident they know what an incidence matrix is? Okay, let's test. How many 1s will there be in every column of this incidence matrix? Exactly 2. Why is that? What does each column of the incidence matrix contain? Each column of the incidence matrix is an edge. There's 1s corresponding to every vertex that touches that edge. How many vertexes touch an edge? 2. So how many 1s are there in each column? Exactly 2. Okay? How many 1s are there going to be in a particular row? Okay? It depends upon the vertex degree. Okay? It's going to be exactly equal to the row associated with vertex v2 is going to be exactly equal to have as many 1s as the vertex degree of v2 in the graph. Okay? How many people see that? How many people do not see that? Okay? Any questions? Okay? Fair enough. Now, given this matrix, there is a unique incidence matrix for every graph. Does everybody agree with that? That it's easy to sort of build the incidence matrix from the graph, and from the incidence matrix, it's easy to go back and build a graph. Okay, it's just an alternate data structure. You could easily write a program in linear time to translate from one format to another. It's not a hard thing. Okay? But so what's interesting about this? For the vertex cover reduction, we're going to want to now convert our vertex cover problem into a integer partition problem, meaning we want to take our graph and convert our graph into a bunch of numbers. Correct? Starting from the incidence matrix, okay, the dimensions of that incidence matrix are going to be n by m, because there's a row for every vertex and a column for every edge. Okay? We are now going to take that matrix and construct a set of n plus m numbers from the graph. These are going to be our subset numbers, the numbers that we're going to build our subsets from. Okay? What are we going to do? There's going to be 2 types of numbers we're going to create. If we're creating n plus m of them, there's going to be 1 number for every vertex in the graph and 1 number for every edge in the graph. Okay? Let's start off in talking about our vertex numbers. Okay? It's easiest to think of these numbers as being thought of in base 4. Okay? You can make them in base 10, but it really doesn't make too much difference. Okay? But let's think about them as base 4 for now. What are we going to do? We're going to take a number, okay, for every vertex, remember, corresponds to a row of the incidence matrix. we're going to take that row and write that row as a number in base 4. How would we do that? Take a look at this incidence matrix. Here was our other incidence matrix. If we take that row, does everybody agree that that row really defines a number? If we think of each one of these, the columns corresponding, each element of that row, as defining a digit in the number. Okay? So it doesn't seem, once you've got this matrix idea, it should be clear we can build a number from each row. The details of our construction are, we're going to build a number that looks like this. It's going to be written in base 4. Okay? For each bit of that number, okay, the ith bit in that row, or the jth bit in that row, we're going to multiply by 4 to the j. That's why we mean we're going to make it a base 4 number. Okay? And there's going to be a column. One of these numbers we're going to sum up for every column in the matrix. It goes from edge 0 to edge, number of edges minus 1. That's how many columns there are. And we're going to add one extra bit bigger than everything else. Okay? So what is our construction going to be? We take the row, interpret it in base 4, and then stick an extra 1 as a highest order bit to it. Okay? That's the basic construction of a row to a number. Questions? Why that 1? Okay? That's going to come from the magic of the proof. Okay? It'll be clear once we get the vertex number. I've given you vertex numbers. I haven't told you edge numbers. But let me give you some intuition here. Why do I want to build my numbers like this? I am now going to, these are the numbers that are going to form my subset, right? I need to have a target number that these all add up to. Okay? If we're going from vertex cover, my vertex cover problem said, is there a set of k numbers that cover these things? I am going to want to collect a total of k of these numbers and add them together to correspond to a vertex cover. This is the intuition now. So what happens if I add up k of these numbers? Okay? The bottom line is, if I add up k of these numbers, there's going to be k of 1s in this highest order column. I'm going to use these highest order 1s to control how many numbers I put in my target. Okay? That's the strategy issue. When you see the rest of the construction, it'll all put together. Okay? Any questions? Okay? These are my vertex numbers. Now, so again, if we take a look at what we're going to be doing, okay, vertex 2 here had 2 1s adjacent to it. Okay? This number will become 4 to the 0 plus times 0, 4 to the 1 times 0, 4 to the 2 times 1. Okay, sorry, let's shrink this thing down. This is going to be 4 to the 2 times 1, 4 to the 3 times 0, 4 to the 4 times 1, plus 1 extra 1 outside, which is going to be 4 to the 5th. Okay? And when we add that thing up, that's going to give us V2. That's, what is that? That's 4 to the 5th plus 4 to the 4th plus 4 to the 2nd. It's a number. Okay? Any questions? Okay? But those correspond to the vertex numbers. We're also going to have numbers corresponding to edges. Okay? The edge numbers, the edge of a particular, the number corresponding to the jth edge is simply going to be 4 to the j. Okay? So if we take a look at our matrix here, okay? If we take a look at our matrix, okay? Remember, each column corresponded to an edge. If we wanted a number just for that edge, the number for edge 3 is going to be a 1 in the 3rd bit and everything else zeros. Okay? The number for edge 1 is going to be a 1 in the first column. Number of edge 2 is going to be a number in the second column, and so on. A 1 in the second column. Question?
1,296.
Okay, so this adds up to 1,296. Wait, 296. Okay, fine. That's what it adds up to. If that's what it adds up to, it adds up to. Okay? But what's the point? We've now got vertex numbers and edge numbers. And the edge numbers are just going to be 1 bit large. Okay? They're going to have a 1. The edge number j will have a 1 in the jth column and nothing else. Okay? So what's the construction? Let's look at this example from the book. Here we've got a graph. Okay? 5 edges, 5 vertices. Here we've got the incidence matrix. Okay? For each vertex of the graph, okay, we are going to come up with this number by making it a base 4 number, adding the 1 on the outside. That's the incidence matrix. There's the 1s outside. Expressing these as base 4 numbers, you get this. Okay? There's also edge numbers. The edge numbers for edge number 0 is going to be all zeros except for the 0th bit. Edge number 1, all zeros except for the bit corresponding to E1, E2, E3, E4, ... Okay? See what we mean by edge numbers and vertex numbers. Okay? Okay, so the edge number, okay, first let's say, how many people understand what I mean by the vertex number construction? Okay? The edge number construction is just going to be, I'm going to have one number for every edge, and that number is going to consist of, for the ith edge, I'm just going to take the bit corresponding to the ith column, okay, and set that one to be 1. Since these are base 4 numbers, this number is 1, this number is 4, this number is 4 squared is 16, 64, ... Any questions about that? Okay? These are my numbers, okay, for my subset numbers. Okay? Any questions? Is there something missing in my translation? What else do I need to create a subset sum problem? I need to have a target number that these are going to be adding up to. My target number is simply going to be the k from the vertex cover problem times my high order bit, okay, plus 2 times 4 to the j for every column j. Meaning that my target number, okay, is, if I do this reduction, going to look something like this. For every column, I'm going to have a 2. Remember, these are base 4 numbers. So I'm going to have 2 in every column, except for my overflow column. There I'm going to have my k from the vertex cover problem. Okay? Any questions about that? Question? This k is, remember, what are we translating? We're translating as input a graph G, and since it's a vertex cover problem, saying, hey, give me a vertex cover of size 3. Okay? Or less. Okay? I'm going to translate that, factor in that k over here by adding k times the largest, the high order overflow bit. Okay? And adding that to my target. Okay, so we take a look at the target number. I'm not sure how clearly that shows up. In all of the lower order bits, there's going to be a 2. This is a base 4. So when I say bit, I mean a bit can be 0, 1, 2, or 3. Okay? And an overflow of base the target number times 4 to the that. Okay? Any questions about that? Now, why do I do this? Okay? Let's think for a second about what property these numbers have that are kind of neat. How many, okay, we have a set, okay, suppose, let's say, okay, I want to have a, what do you call it? A set of numbers that adds up exactly to the target number. The target number has a big first thing corresponding to the k from vertex cover, and then 2's everywhere else. Okay? How could I get a subset of these numbers that will match that? How many numbers can I pick which have this big first order bit in it? K of them. Okay? If I pick k numbers here, okay, then I can guarantee that when I add them up, I'll get roughly something that will match that first bit. Okay? Clearly, if I pick more than k of them, my number is going to become too large. Okay? And I very cleverly made these things base 4 numbers, so that things wouldn't carry over. So the only way that I can get a subset of these numbers to be roughly equal to my target, to be even close to my target, is going to be by picking exactly k numbers that correspond to vertices. Okay? How many people believe that? Okay? How many people don't believe that? Okay? Let's take another look at this thing. I designed my target number to have two pieces, two sort of sets of, have sort of low order numbers and big order numbers. The big number is going to be k times the 1 I added in a high order bit to every vertex. Why is that? If I pick some subset of these vertices, okay, if I want to make it equal to my target, in order to get enough stuff to be equal to the target, okay, I've got to make sure I pick k of these vertex numbers, because I have these vertex numbers have this big first piece that's 1 times my the field where I'm going to have my vertex cover number. Okay? If I pick exactly k of those, k times that 1 is going to be equal to k in the appropriate position. So by picking a set of k vertex numbers, I will be able to get that high order bit part of my target number matched. Okay? Doesn't say anything about what's below it. Okay? But it says that I will be able to get it matched. Okay? Any questions about that? How many people believe that now? How many people do not believe that? Okay? No one says they don't believe it. Okay? Now, the secret is that I've done this in such a way that the only way to realize it is by picking k vertex numbers. Picking more than k vertex numbers should obviously create a number too big for my target. Picking less than k, because of my carries I can show, will never cause me any trouble. Okay, so I can't make it up that way. Okay? So what do I have to do now to match my lower order bits? What are the lower order bits of my target all equal to? 2. How many 1s are there, okay, in any column? Okay? There were 2 because it was an incidence matrix. And now there is 3 because I added 1 extra number corresponding to each edge. Correct? So if I want to get these numbers to be equal to 2, those bit fields to be equal to 2, what do I have to pick? How many of those 3 numbers that contain that bit field do I have to pick? Exactly 2 of them. Okay? Remember, these are base 4 numbers. The most numbers, the most bits in any if I took all the numbers with high bits, I could get at most 3 of them. There's no way I can add 3 numbers and overflow that last field. Okay? So I'm not going to be able to get any help by adding up a lot of things and having things carry over to balance things out. Instead, what I've got is a situation where every row, okay, corresponds to a, where for every column I've got a 2, okay, is in my target. The only way I can get that is by picking 2 numbers that have 1s in that field. Okay? Does everybody, how many people agree with that? How many people do not agree with that? Are there any questions? Okay? So now maybe things are starting to become clear. How can I get a 2? If I demand a 2 in this lowest order bit, how can I get it? Okay? I could pick 2 vertex numbers that happen to have those be the 2 endpoints of that edge. That would give me 2. Or I could pick one of the numbers that contains that endpoint. Okay? And my extra floating edge number. Is there any way I could get a 2 in the lowest order bit without having one of the 2 vertices corresponding to the vertices that touch that edge? Okay? Is it possible? No. Okay? The only way to get this 2 is by either having both of these vertices or one of those vertices and my floating number. Okay? How many people see it? How many people do not see it? Okay? Any questions? Question?
The only confusion I have is, I pretty much follow it. Where did we get the 2's across the bottom?
That was part of the number that we created. This is the target number we created. If you go back to my other slide, okay, I said that my target number, which I'm constructing in advance, is equal to k times my highest order possible bit plus, for every bit corresponding to an edge, 2 times 4 to that bit, which means put a 2 in every one of those fields. That's where those 2's come from in the target. And the reason we did that was to show that that was what was necessary to make the match. Okay? So what am I claiming here? Okay? If you give me a vertex cover of size k, what is a vertex cover of size k? It's a set of k vertices, okay, 1, 2, 3, k vertices, which have what property do those vertices have? That every edge is touched by one of those vertices. If you take those k numbers corresponding to those k vertices, and add them up, what are you going to get if you just add up those vertex numbers? Okay? You're going to get a number that's going to look like k in the highest order bit, then either 1's or 2's in every other field. Because we've covered every single edge. Okay? Once, maybe twice. If we covered it once, we got a 1. If we cover it twice, we got a 2. If we've got a 0, you lied. You didn't give me a vertex cover. Now, once you give me this, how can I finish completing my subset of numbers in order to make things match? Whenever there was a 1 in the sum that you've given me so far, add that corresponding edge number to it. And that will then turn that bit to be 2. And I can freely select exactly the edges that I need in order to make the target what I want. Okay? So bottom line, what am I claiming? Okay? Let's now look at the if and only if reduction. If you give me a vertex cover in that graph, I can find a integer partition of those numbers, or a subset sum of those numbers adding up to my target. Why? You give me k vertices that cover it. I'm going to pick those k numbers. Every edge is incident to 1 or 2 cover vertices. If it's 1, that's good. Okay? I'll add that extra edge and make me match the 2 in my target. If it's 2, I won't add that edge. Okay? If you give me a vertex cover in the graph, I can find an integer partition subset sum solution. How many people believe? Okay? How many people do not believe? Okay? Question? Okay? If you give me a vertex cover in the graph, here's my graph, pop, 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 graph. Okay? And you're giving me now a vertex cover of this graph. Okay, with k vertices. I can now find a integer partition or subset of, I'm now going to construct a subset of those numbers by picking the numbers corresponding to the vertices and then up, seeing where I've got my 1 bits, and then picking up the extra edge numbers for my subset also. Okay, I cannot have a 0 in any column, because if you gave me a vertex cover, that subset of vertices you gave me had to touch every edge. If you gave me something that wasn't a vertex cover, well, then that's not true. Okay, but that's not what I'm saying. If you've got a vertex cover, then a subset of numbers that I can pull out easily that matches that vertex cover. Okay? Question? Okay, what is the point? We now have to show that if there is a vertex cover in this graph, then there is a integer partition in this graph, a subset some solution. If there is a cover, I'm saying you show me that cover. What is that cover? That cover is 3 vertices. Okay? Each vertex here corresponds to a vertex number there. Okay? Now, if you give me this vertices, I can now construct my subset sum solution for this. Because I'm going to take exactly those numbers you gave me, add them up. Is it hard to add some numbers together? No. Add them up together. Look at the digits of what you get. Each digit corresponds to how many edges, how many times have you covered each edge. Digit I corresponds to how often did you cover edge I. If you had a vertex cover, you covered it either 1 time or 2 times. If you lied, you covered it no times. But then I can see you lied. I added it up and said you lied. Okay? So that's not a problem. If you gave me a vertex cover, when I add up these numbers, I have to have 1s and 2s. Now I'm trying to prove that there is a solution that matches the target exactly. And why? I've got for every edge number column, I've got an edge number floating around, which I'm free to pick, which is exactly equal to a 1 for that bit. Anytime I want to convert those 1s into 2s, just add that edge number. And I'll add exactly the edge numbers that I want to do the job. Question?
Now you showed us that in polynomial time you can find a solution for the integer partition if you have a solution for the edge cover. But I thought we wanted to use integer partitions in order to
What we need to show is that the reduction preserves the truth of the answer. That there is a solution to my integer partition problem if and only if there is a solution to the vertex cover problem. Correct?
Yeah.
So I have to show the reduction 2 ways. First of all, that if there is a vertex cover, if you give me a vertex cover solution, I can find my integer partition. That I just did. Now the other way I've got to do is now show that if you give me an integer partition solution, that will give me a corresponding vertex cover solution. And if you think about it, you got to know what's coming. Okay? My integer partition solution consists of what? A bunch of numbers. What kind of numbers could I have added up? Some of them were vertex numbers. Some of them were edge numbers. Throw away the edge numbers. Okay? Just take the vertex numbers. Find out what the label of those vertex numbers are to figure out which vertex they corresponded to in the graph. Because what do I know about these vertex numbers? There had to be k of them, because k was my highest order bit. I couldn't realize it any other way. So you've got k numbers now. They're all vertex numbers. Okay? It's true that when I add them up, in every column, there had to be at least a 1 or a 2. Okay? Couldn't be a 0, and there couldn't be a 3. Okay? Why? Because, again, if those numbers added up to 0, there's no way I could have made it 2 by adding an edge number, because the only edge number that I could have helped with only accounted for one of them. So if you had a target, a set of numbers adding up to the target, it had to, okay, consist of k vertex numbers, each of which together covers a column. Okay? So if I give you a solution to this integer partition, that gives me a solution to vertex cover. Okay? My reduction means a solution to vertex cover is the same as integer partition the same as vertex cover. Our reduction preserves the truth. The translation happens quickly. Okay? It's not a hard translation. Integer partition is neat, sweet, and NP-complete. Okay? Any questions about the reduction? Okay? How many people see the flow of the argument? Okay? How many people are confused at this point? Okay? Some people are beaten into submission, maybe, but not confused. Okay? Any questions? Okay? Question?
So far we always only showed in one direction.
No, you've shown in both directions.
Yeah, in this problem.
In all problems, I've shown in both directions. Okay? You've got to be careful to show in both directions. Okay? But if you look back, I mean, I've done that in all of them. I haven't been cheating in that. Okay?
So the solution we show in both directions, but the mapping of the input problem normally only in one.
Right, the mapping of the input problems. You're mapping all vertex cover instances to integer partition instances. You're not necessarily going the other. You're not doing anything about all integer partition instances. But whenever you've done the mapping, the answer between the original graph solution and the integer partition you mapped it to is exactly the same. That's what I've proven. And that's what I've proven for every single one of them. Okay? And that's the key point. The answers have to be the same. Okay? Any questions about that? Okay? Very good.
So wouldn't this be a lot easier if we now just make these two problems decision problems?
Wouldn't it be easier if we made the two problems decision problems? But they are decision problems. Okay? What is the subset sum problem? Given a set of integers and a target, is there a subset of numbers that adds up to a target? What's the answer to that question? True or false? Okay? So that's a decision problem. Given a graph and an integer k, is there a vertex cover of size k? Is that a decision problem? Okay, and what did I just, yes it is. And so what did I prove? The answer to the translated subset sum problem is exactly the same as the original vertex cover problem. Any questions about that? Okay, very good. Okay, at this point what I'd like to do is stop a little early and pass out the course evaluations. Okay, so hold on a second. I've been carrying these around for a while. Okay. Let me, camera can probably go off for this unless you want to film people's evaluations. I might be interested in that, but I don't know if other people would be. Okay, so let's pass these things out.